All right, welcome to the Roman-Numeral-Calculator-Kata done in Kotlin. I'm actually going to start from scratch, as in creating a new project in IntelliJ, which I think is valuable to see. So let's go ahead and open IntelliJ. All right, the first thing we're going to do is create a Kotlin project. So create new project in IntelliJ. It'll give you a couple of options to do that. Now there's a Java option here for Java project. There's also a Gradle option here. What's the difference? Well, using the Gradle and then using Kotlin JVM, we'll be using IntelliJ to create the initial scaffolding. Whereas if we did just Java and went down here and choose Kotlin JVM, it's more bare bones. All this is going to do is just create a Java project with the Kotlin JVM library, and that's it. I actually like this route, so let's click next. And so we'll name our project Roman. Which will also become our package name, because as you remember, Kotlin compiles down to Java, which is why we're creating a Java type of project. So this project name will become our package name as well, our Java package name. All right, let's double click this bar, make it full, expand. And now notice there's not much really here. What it did add for us is the Kotlin runtime, but we really can't start our Kata unless we actually have some scaffolding, some initial build using the build Gradle. Our Gradle build, I mean. So let's actually use Gradle to initialize some scaffolding here. So let's do Gradle init. Which will give us some nice options to start some project types. Since we're doing a Kata, we don't need a Kotlin application, so we'll choose number 9, a Kotlin library. It's asking us what kind of Gradle build file do we want. Groovy is the standard one you see in Java. We could use that, but I'm going to use number 2. Which is Kotlin syntax, and it gives you a little better IntelliSense in IntelliJ if you use the Kotlin Gradle build. I'm going to keep the project name, which will become our package name, hit enter, and let's see what it gave us. All right, so it gave us some initial scaffolding. We got our production code up here, which you typically see in Java, but it gave us a Kotlin class. It also gave us a Kotlin test. Notice we can't run this test yet. Usually there's a play button here in IntelliJ. Problem is IntelliJ does not know about our Gradle build yet. Yes, we have files in here, but IntelliJ does not know about the build. We have to kind of tell it, and that's fine. That's kind of what I wanted to do. I wanted bare bones and to kind of wire this up myself. So let's right click the Gradle build file and go to the option import Gradle project, which will marry up IntelliJ with our Gradle build. If we click OK, it will do a build for us. Notice it also gives us a Gradle pane over here now. Since now IntelliJ knows about Gradle, it provides some nice functionality over here to run tasks if you want. You can still run those tasks from the command line using the Gradle CLI. You can do that too, which is usually what I do. Now we can actually go back to our test and notice that we can actually run it. So we have a play button here. Let's go ahead and just make sure we can run our test before we start our Kata. Excellent. All right, let's get started. We actually want to rename this test. Actually, first what we want to do is get rid of this because we're actually going to test drive this production code. So let's do command delete and get rid of that. Second thing we want to do is we want to rename this file. So we're going to do shift F6. It's actually shift function F6 for me on this keyboard. All right. Now, one thing I'm going to do, I'm going to blow this away because I have my own code snippet I set up for myself, or what they're called in IntelliJ are live templates, which basically means code snippets. I've created my own. So what I created is this Spec Kotlin, because I use certain Kotlin test classes, certain frameworks I like. There's a few ways you can do Kotlin tests using JUnit. This is what I like to use. Let's name this the same as our file name, Roman-Numeral-Calculator-Test. Let's make sure we can run our tests again. We can run a test. Let's do a Control-R to run the test again. No tests were found. That's because, let's get rid of this. So if you go up here, let's get rid of this configuration. Now, if we click this play again, it will create a new configuration for us at the top. Watch this. And this is how IntelliJ knows how to run your tests. It creates a configuration on the fly. And here you can tweak stuff if you need to, but now it actually knows about our test again. I think because I changed my code snippets, it kind of messed up the existing configuration, so now it's good. All right, excellent. Let's actually write our first test. Before we start, there's a couple things I want to do. First, I want to get rid of this project pane here. Second thing I want to do is I've got a little hint down here you're seeing when I type. You're actually able to see what I type, but I actually want to move it over. So I'm going to move this little hint over to the corner so it's out of our way. All right, let's run our first test. The simplest test we could write would be 1 + 1 is 2. So we are going to do some wishful thinking here and hope that we have a calculator, which we don't yet, but we will be creating. So total, we'll use a calculator, and we're going to add those 1 and 1 together to get 2. So I and I. So we expect that we get back 2, which is I from total. Let's run our tests and see them fail. And our first failure is a compile error because we don't have a calculator yet, so let's go ahead and create it. Option Enter, create a class. We want to put it in a certain place. We don't want to put it in our tests, so we're going to tell it to put it in the production folder. All right, now we have calculator. Second thing we need to do is to add an add method. We don't have that yet, so we do Option Enter. Whoops. Option Enter, create that. Now the fastest way to get this to pass is to literally, well, first we want to see our test fail. So let's return a null. And in Kotlin, we need to change this to be an any. And let's run our test to see it fail first before we actually make it pass. Now we're actually failing. We're getting a failing test. So we've got our compile errors out of the way. We've got a failing test. Let's make this test pass. So fastest way to make it pass is to return a hard-coded string, which means we'll need to change this to a string here because we're returning a string now instead of null. Let's run our test. Excellent. Before I start our next test, let's actually split our pane here so we actually see the production code with our tests at the same time, which is easier to see. All right, next test. 1 + 2 is 3. All right, so to make it pass, we can use a simple string template in Kotlin, which goes like this. That should do it. All right, so let's do some refactoring. This variable s doesn't make any sense, so let's call it Roman-Numeral-1. Let's call this one Roman-Numeral-2. That's better. Let's run our tests. Still passes. Let's do some refactoring on the test side. We've got some duplication here. The calculator. We got some duplication with the total. So let's actually move some of these into variables. Actually, we don't need new in Kotlin. All right, so now we can just do that. Just run it again. Should pass. All right. Okay, our next test. == 5. Okay, let's do some refactoring. I see some duplication here. Let's move this out into a variable. We want to place both occurrences into a new variable called, let's call it total. All right, let's run our tests again. Excellent. Before we start our next test, I actually noticed the compiler complaining, well, a warning, giving us a nice hint. So let's do option enter on this and make it private. All right, so that's nicer. Not that it matters in the kata, but I like to have my code clean as possible. So next test. 5 plus 5 is 10. So what we could do to make this pass is to simply do another if statement. So if we said VV, we could return X. However, Beck says one of the things you can do is make your code better for your next test. So let's actually back out and do that. What we could end up doing is refactoring both these if statements. But actually what I want to do is do a little more refactoring first to make this test easier to pass. So let's actually back this out. Let's go ahead and comment this out. Let's actually move this into a lookup table. So we're actually going to introduce a map in Kotlin. And we're going to move this into a lookup table, this value here, the key value pair. This will allow us to clean up some of this. We can actually run to Roman total. Run our test. The problem here is that Kotlin's saying if we don't find anything in the lookup table, we can't return null. We need to return something. So if we don't find it, let's return the original value. So we'll do a, hey, if you don't find it, return total. Okay, great. Let's actually go back to our next test. And now you'll see how easy it is to actually pass this next test. Let's run this again, see it fail. Now that we have a lookup table, all we need to do is add another entry to it to make this next test pass. So VV should equate to next. Let's run our test. Great. All right, next test. All right, so it fails to make this pass, just another lookup value. All right, so now I can handle 50, adding 50. At the moment, I don't see anything else to refactor, so we'll move on to our next test. Okay, next test. All right, fails. Let's make it pass. All right, so these first few tests gets us the lookup table for the main numerals we're going to be using going forward doing more complicated combinations. So we've got the V, X, L, C, D, and M available to us to now move forward with more complicated tests. All right, so now we can get into more of the business rules or the behavior of this kata. The first piece of behavior I want to focus on is the rule that says only one subtraction can be made per numeral. So to force us to implement that rule, I'm going to do this test. All right, let's make it pass. Let's run it. We're going to change this, and I'll explain this in a minute. So we wrote only enough code for this simple use case based on the double i's we're sending in. So we can't subtract two i's. So you can't have two i's before the v. You can only have one i. So we check to see if we've got more than one i, count is greater than 1, and also if the Roman numeral runs different from Roman numeral 2. If they were the same, we would just pass the 3 i's back. Say there were 3 i's, we would just return it. But in this case, the Roman numeral 2 is a v. So we know that we are adding two different things together, two different kinds of characters. If we're trying to subtract 2 i's and number we're adding to 5, then we need to swap it and make those i's addition. So let's actually refactor now and make this a little more meaningful to anybody reading our code. First thing we can do is in the if statement, this behavior, this check here, we can actually name that. So let's do that. We can name that to be something like is illegal subtraction. We could also name it something like is subtracting more than one of same character. We could also name it that too. I'm just going to go with this for now. It's a little more broad. It might have been better to go more specific, but for now we're just going to keep it like this. We can also, so that reads a little bit better. Hey, if it's a legal subtraction, but let's actually put this into a method as well. So what we're going to do if it's illegal, we're going to convert the legal subtraction to be addition. I don't like how IntelliJ did this, so I'm going to change a couple things around here. I actually want to change this to be a string because I actually want this to return what it says it's going to return, which is convert illegal subtraction to addition, which is going to be the string reversed. So return the string reversed, basically. All right, so if it's illegal, return the string reverse. So return let's get rid of some spacing here first. All right, it's a little long, but for now we'll keep it that way. This got all jumbled up. Let's put this back like it should be. All right, so if it's a legal subtraction, then we're going to return it converted to be addition. So run our test, make sure your refactoring worked. Actually, one more thing we can do is, so this is up to matter of style. I see it as a matter of clean code. Now I could just leave it like this, and it's kind of obvious what we did, but maybe some people don't understand what we did. So let's move this to a variable. Let's move this into something like combined something like that. So I like this better. It explains my intent of my code better. It means that we reverse the inputs and we're returning them. So in our test, it all passes and we're good. All right, so now we got this table where we can convert some sequences of characters that are the same to another character. But let's do a mix of characters. What if we have a mix, say a sequence of characters mixed in with something else? We should still be able to do some find and replace on those sequences still. So let's run a test to force our code to be a little smarter using this table. So I'm going to do 6 plus 6 is 7. Alright, so let's go ahead and make this pass. So for each item in the table, let's do a find and replace on the total string. So if we find a key in the string, find one of those values, replace it with its value. Problem here is total is immutable. Let's make it so we can actually change it. And this should hopefully run and pass. Alright, so what we just did is sent in 6 i's. It found a match with 5 i's here, and then converted that to be a v. And then the rest of our code already flips the v and I. So let's see if we can do some refactoring. So in production code, let's make this more meaningful by moving this into a method. And based on what this is doing, it's replacing number matches basically. So I'm gonna name it something like that. Replace numerical matches. So in our test again, see if they pass. All right. So before we go into the next test, I actually see an opportunity to refactor. We've got an if statement here. We can move into a method with a better name. So what this is basically doing is saying, if it's illegal, swap and make it an addition. So swap for except that's not what I actually want to do. I didn't refactor the way I wanted it to, so let's actually do this manually. And we can move these 2 lines down into it. And then we can have this actually call it and then just return it in our method here. This should pass. Oh, I forgot to change this to 2. Let's run it again. All right, there we go. All right, so the next rules I want to focus on are the symbols V, L, and D can never be subtracted. So I'll just write a test to force some of that behavior to start happening. 5 plus 10 is 15. Let's make this pass. So basically what we can do is iterate on this is illegal subtraction here. So there's several rules that make it illegal. We're introducing a new rule that says you can't subtract v. So let's just make a simple thing here to make it pass. Since we have more than one statement, we have to change the syntax of this function. We had return there. What did we have before spec up? We messed up. All right, yeah. So it was doing a implicit return here, but now we're actually telling it to do more than one statement in Kotlin. So we need to tell it to return explicitly. All right, so notice that our new rule here. So I'm going to take this quite literally this time. So if all right. Okay, so that accounts for v. Let's do the next one, which is you can't subtract L. So let's do a test that will force us to deal with L if we're subtracting it. 50 plus 100 is 150. Okay, so I could literally copy this and like basically create another line with the same thing and just make L. But what I'm actually going to do is back up and do a little more refactoring in the previous test to make this test easier. This is one of Beck's things. If you can refactor a little more to make your next test easier, go ahead and do that. So we're actually going to do that here. So I'm going to back up, and what I'm going to do is I'm actually going to change this entire line. I just realized that I think I don't even need this part. Let's see. Let's run this. Yeah, so I didn't need that. But let's also refactor more. Basically, if the first Roman numeral that you're adding has v in it, means you're subtracting illegally. So that qualifies as an illegal subtraction. So let's change this to be list of v and say that let's filter, say that if it's in Roman numeral 1, then we know it's illegal. So if Roman numeral 1 has v in it, then we know it's illegal. So let's run this and see if it works. Now you're going to see how this makes our next test easier. So if we uncomment this, so not only did we refactor, we simplified it too. I took out some stuff I didn't need that I realized. So let's run this now. Now all we have to do is put in L, and that should pass. Because if L is anywhere in the first numeral, in the numeral 1, then it should detect that it's illegal. It's an illegal subtraction. And there we go. And the final character we can't subtract is D, so let's write a test to force us to deal with that rule. 500 plus 1000 is 1500. All right, so in this case, we just need to add d to it. Okay, so there's a couple cases where this rule won't actually cover everything. So we just did coverage of illegal subtraction of v, l, and d. But what if we wrote this test? 5 plus 1 is 6. So the problem is vi is actually valid as 6, but because it detects that v is before I, it swaps them and actually makes it 4. So we actually need to put a special rule in here to detect this case. So if we go back up to here, now I'm thinking ahead, I'm actually going to need to use this, I think, to solve this. But right now it's not exposed, it's in this function here. So I'm actually going to, again, back up, refactor a little more, so that I can actually get to that a little easier. So if I do this refactors out to be a combine inputs. All right, so that actually replaced it here as well. So we're actually reusing it, which is nice. All right, so now that we have combined inputs here as a method, I can get to it for my next test to try to make it pass, because I know I'm going to need it. So if I undo this, now run this, because what I'm going to do is I'm going to say, just for this particular case, I'm going to say if it's vi, don't mess with it, just return it. Just keep them the same. You can concatenate and return it. Because that's okay if you do vi. Whoops. Actually, what I wanted to do is, if the combine inputs is vi, return the combine inputs. Basically, this should pass it right here. Just return the same thing. Now, let's actually do some refactoring. Let's actually move this right here into a variable. Call this total. So if total is vi, just return itself. Problem is we've been using down here, so let's actually get rid of this and make this a var up here. There we go. Oops, got to do this. All right, so this should pass now. Excellent. So that covers this special case, but there's a couple other cases where we don't want to swap if it's illegal because it's actually a valid addition. So the other one would be, let's say, for example, we did lx, which is 50 plus 10 is 60. We don't want our algorithm to swap it to be xl if l plus x is 60, so let's do that one. But again, I see an opportunity to refactor again to make this next test easier, which is kind of what we did before. We did list of. So let's do that again. So if we do list of vi, put this in a list. So this is just saying, hey, in the list of illegal or of special cases, if Roman numeral run equals, oops, actually I want to do total. Change this a little bit. Total equals it. All right, let's do it. So our tests. So I've just put this into a list. So the next test, we should make it easier for our next test to write less code and make it pass. So if we do 50 plus 10 is 60. So here, we'll just tell us not to do anything for the special case, and it should pass. Excellent. Now there's a third case, which is similar to this, which is DC. So D becomes before C, but it's really not subtraction because we're actually saying 500 plus 100 is 600, so we need to keep it DC. Don't swap it. So let's do 500 plus 100 is 600. Should stay the same. Well, because it detected a D, it's going to swap it. So let's tell it not to swap it in this case. So we'll just add a DC. So what is this actually? Let's actually refactor. And what is this actually doing? This line? Well, it's saying to basically, in these cases, ignore subtraction, the subtraction rule, and just return it back, because those are the cases that are valid and they're actually addition. So let's refactor is to say ignore illegal subtraction. Now, it's the best name I got for it so far. We can rename it later. Oh, let's do this again. Ignore, spell it correctly. So that should take care of this. Let's run our test to make sure our refactoring is okay. All right, excellent. So that takes care of these special cases. The next rules I want to tackle are the symbols I, X, and C can only be subtracted from the two next higher values. For example, you can do IV, but you can't do IIV or IIIV, or you can do IX, but you can't do IIX, stuff like that. So let's tackle that next. All right, so let's look again at the order here. If we look at how this all works for this next set, we can subtract I from V, or we can subtract I from X. We cannot subtract I from L. So let's do that first case, I from L. Actually, I can't write the test this way because the output's going to be something like illegal subtraction. So let's kind of do all the cases in this test. So let's actually name this something like can only subtract from next to highest values. And we'll start off by doing the first case. So total goes. We expect it to return an illegal operation error, so let's do this. All right, so let's make this pass. So taking this test literally, we'll do should make it pass. All right, so let's do the next one, which is I and C. Again, I'm going to convert this, I'm going to do some refactoring and put this into a list. So let's do that. Let's do All right, so next test. We can't do I and D. All right, and finally, we can't do I and M. All right, so this is all fine and dandy for the case of I, but what about the rest of the cases? What if we have V? We can't subtract V from C or V from D or V from M. So let's actually start with V. Try to get this, we're not done with the logarithm yet for this. So we need an assert that'll try to make this fail. Because obviously this isn't handling all cases yet, so let's do this. So we can't do V plus C, because C is 3 places in order of precedence ahead. C is 3 higher than V. That should fail. And it does. Now, I can add yet another, I could just do this. And it will pass, but we keep, these are all hard-coded. So I want to make my production code generic, not so specific. I want to be able to make this code work for many other cases besides just I, without hard-coding every other case in here. So we can do a bit of work here. I think what we need to do is pull out the order of precedence. So first what we can do is, we know that we're comparing each of these cases to the full list of ordered characters. So let's create that list. Alright, so we've got the order of precedence basically that we're looking up to make sure that we're not subtracting more than 2 of the next higher values. So if we've got a total of combined inputs, what we can do is we can compare the characters in sequence. And if at any time we have one character that's more than 2 below the next character, we know that we're trying to subtract too far. So let's go ahead and make this a little more generic detection. So if we do total.forEach, actually if we do toArray, toCharArray.forEach, forEachIndexed, which allows to work with each index of each char in the array. So I want to get an index of each of the characters, and with that, so if we get each index and we find out what index they are in precedence, so we find out what order of precedence they are, which is the current precedence for this current character, when then we get the next precedence, we can compare them. So if we do val next char precedence, actually what we're going to have to do is introduce a previous. Actually, let's do this first. Let's do so basically we're looking ahead here and getting the order of precedence for the next character. We'll populate that in a second for this previous char index. So here we're saying the next char precedence is the index of the previous char index plus 1. So it gives us the next character in line and its precedence. So to get this previous char index, we need to set it to the current char. So actually we need to introduce val our previous char index. Initialize it here, and then we can set it at the end. So now we can actually compare the current character in the total with the next characters, so I can get their precedence and compare their precedence. So if next char precedence minus current char precedence is greater than 2, the next char, so if we've got I, the next char is V. Okay, if we have I, the next char is L, we know it's 2 higher than I, so that's not legal, so we're going to have to return that error. So let's just here, return. I'm hoping that this will let us get rid of this entire line. So if we run our test now, it doesn't. Let's make sure that this actually works just for what we had before. So if we do run this, it does not. Oh, we missed C. We've got to put C in here. So let's do, after L, we missed C. So C, I think that's what it was. So that's what we're missing here. IVXLC. Oh, I see it. I should move this inside here. Outside. Run the test again. All right, cool. So instead of hard coding every case, no, we're now looking at we're cycling through each character, the combined inputs, and looking at the current character, looking forward to the next character, and finding out where in the order of precedence they lie. And if the character ahead is more than 2 higher in precedence, then we know we can't subtract it. So we can now get rid of this. And let's refactor this into a method. So first of all, let's refactor slowly. If you go back to here, this means basically we subtracted from more than 2 next highest values, basically. Then we'll return new operation. You can also move all of this stuff to be inside. Basically, let's just move stuff inside that method. It's going to be part of the behavior of this method here. So we can actually move this up to be here now. Oops. Yeah, we could do this. Combine inputs. Change this to be I'm just changing it around. All right, this should still work. All right. All right, this should still work. So let's run this test. And it does. Okay, so now if we uncomment this, this should be taken care of now that our code is more generic and it's doing a lookup based on order of precedence. So let's see if this works. It does. Now what we can do is refactor our tests to be a little more efficient. So we can actually refactor and then account for the rest of the use cases for this behavior. So one thing we can do is, instead of having all these asserts, let's do this. Let's put these as pairs, each one of these use cases here. We're kind of cleaning up our test here. M and let's see, is that one? Yeah. All right, so let's get rid of this here. We'll do this in a minute. Let's see, and then what we're gonna do is we're gonna cycle through each of these, one of these illegal adds and assert on them. So we'll basically make our test nicer. Instead of having all those asserts, we can just do it. Just do a list of legal adds and cycle through them, and then assert on each. Let's also refactor this here, give it some meaning. So basically, this is saying the difference is too high. So we should be able to do the other cases, so let's try that out. All right, so the next rule we'll tackle is, only one subtraction can be made per numeral. So you can do XC, but you can't do something like XXC. So let's write a test. Let's start off with a simple assert. Let's try to do total something like this. We can't do that. But really what's happening here is, yeah, we can't do an illegal subtraction. We can't have 2 i's or 3 i's. But what they're actually really doing here is addition. So CII is really what we should end up with. We shouldn't have an error on this one because we can actually produce a valid result by making this an addition. So we'd expect to actually get this. So don't throw it away, it's still good, but just swap it and make it an addition. Let's run and see if we can get this to fail. Actually, let's do a different one. Let's do IIV. Maybe this will make it fail. Oops, actually no. VII. Sorry, VII. I get the wrong test here. All right, let's run this again. I'm not sure what I was doing. IIC. I meant. Oh, what? Is this passing? Let's try this. Well, maybe we're good. No, we're not good. So in this case, oh, we're good. I've got to change this. So I think we might be okay. All right. So this is actually taken care of. This rule's already done. It's something we don't have to even deal with. So that's good. Let me just change this around a couple more times. Just to be sure. All right. I'm going to stop the kata here. I'm not quite done, I don't think, but we've gone long enough, and I hope you learned a few things. I know I did. Thanks for watching.